Welcome in. All right, so let's take a look at a few examples that will slowly gear you into kind of kinematics. So just kind of thinking about some of the introductory items that you should be aware of. And this is typically for some kind of a course which is introductory on the physics side. So maybe grade 11, so maybe your first physics course somewhere else. So let's take a look and dive into several examples. So here is one example. So it says find the rate of change, which is the slope that we want to be able to find for each time interval. And we have three intervals. So for A, and this is between A and B. And if you take a look at this, so we have A over here and then B over here. Now, do keep in mind that because this is on a graph, just always take a look at the X and the Y axes and then just make sure to see what the units are if they give that to you. So this is your time in seconds, and then this is, it looks like your position, with regards to meters, and it is going east. All right, so let's dive into this. So how would we solve this? Well, so for part A, what we need is that any slope is just simply your rise over your run. So that's what you would have in terms of your standard definition. So if you wanted to be able to find what that is, well, so we're going to be kind of rising up. So this is going to be kind of rising up from here to here. So we're going upwards, and we can see that it's going from 0. And then you can look on the left-hand side there. So the numbers are a little bit smaller, but it goes all the way up. So from 0, and you can see here, that it basically goes all the way over here. So we have 8, 10. So this looks like it's going to be 9 because I can see that we have 1, 2, 3, of those, and it's right in the middle. So we have 9 as it's going up. So that would have been the change, right? So this is the actual change, right, in your position that you have. And that particular change in your position, so we would designate it as delta D, and that is nothing else but simply equal to 9. All right, so you would have 9 meters, and this is still on the east side because we're going up. Okay, so that's what we would have there. Now on your run, so with regards to your run, so what we would have is we would be going from here to here. So that's your run as you're moving along, and then your run would have been the change in time that you are dealing with. So that would have been 9 and the change in time. So again, you can look at the x-axis. So it goes 2 and it looks like it's in the middle. So it looks like it's 3 seconds. All right. So if I'm going to keep the actual units there, so this is going to be meters. This is going to be seconds. So that's what I would have there. And it is with regards to east. So that would have been the direction. So therefore, so 9 over 3 is nothing else but just 3. So this would have been 3 meters per second. All right. And you can put the direction there, kind of east. But if you're just thinking about the actual slope, itself, so there you have it. So that would have been 3, and then you have your attached unit. So let's take a look at another one. So that would have been B. So for B right here, so it's going between, in this case, as you're moving along there, so for B, so what you have, so that is just this flat line. Now, what do we know about flat lines with regards to slopes? Well, that there is no change, right? There is no rate of change at all. So the slope is actually 0 because there's no rise, or at least rise is equal to 0. And then the run itself, it doesn't matter what it is. So in this case, you can see there that it goes from 7, all the way, from 7, and then I guess from 3, so it would have been for 4 seconds. But because there is no rise, then this is just simply equal to 0. So there isn't really much to do here. So this is just 0, and because they're giving it in meters per second, so I'll just leave that right there. And the direction is irrelevant, in here. But in terms of the actual slope, it's just 0 because it's a flat line. Now, let's take a look at the last one. So this would have been C. And for this one, so what we're going to be trying to figure out, so we want to be able to figure out this particular item. So it's from C to D. and we want to be able to find what the rise and the run is. So now if you're going to be doing this, I mean, the easiest thing to do is notice that you are coming down. So you're going to be, your rise is going to be negative actually. Okay, and you can see there that that's where you move over, and you know, you can map this off all the way. So if you're looking at the y-axis right there, so notice that this looks like it's going to be a 5 right there. So it goes, now be careful here because it goes from 9 to 5, right? So the actual change, okay, within your position, so within here, so that change, right? So in terms of your rise, it's going to be negative, and in this case it's from 9 to 5, so it's going to be negative 4, right? So that's meters per second, okay? Sorry, negative 4, so it's not seconds yet. Okay, let's be careful there. So that's just dropping negative 4 meters, okay, as you're moving along. All right, so now what about, okay, so as you're kind of moving along in here, and so this is with regards to your run, so maybe, you know, we'll put your run over here. So that goes in, and it looks like it's, you know, so if you would drop this all the way down, so this looks like it's, you know, 7 seconds, okay, and then if you drop this all the way down, all the way, it looks like it's 10 seconds. So that change, and that would be the change in your time, it looks like it's 3 seconds because it's 10 and 7 right there. So that would have been 3 seconds. So now if you want to find the slope, we need the rise over the run. So if we do that, so our slope is equal to, so that would have been your change in delta D, and this is your change in T. And so for this, so your rise over run, so this was negative 4, this was actually 3 right there, and this is still meters, you know, per seconds. And now it is with regards to east, okay, as you're moving in, because all of the positions that you grabbed, okay, were actually on the east side. Now with regards to rounding this, so if you wanted to be able to round this off, okay, so as you're going through this, you know, you can certainly leave this. It doesn't tell us to round anything, so for each interval. However, you know, if we are rounding based on the fact that we really just have one significant figure in each of these, then this would have been just 4 divided by 3, which is 1.3333, etc. So this would have been kind of repeating. You can put a bar in here, and this would have been meters per second. But if you wanted to 1 sig fig, it's actually just only 1 meter per second. All right, because this has one significant figure and this has one significant figure. But the idea behind this question is, you know, can you actually look at a graph or look at the slope and then just calculate the slope? You can even ignore the actual direction for the moment, okay, and just be comfortable in doing your rise over your run. All right, so that's one question. In this question, we want to be able to find the area. Now it says, you know, provide the unit in your final answer. Okay, so we'll think about the answer as well. Now, given that, okay, so it's providing us kind of 3 items. So we want to find the triangle ABE. So that particular triangle, so as you can see here, I'm going to just kind of sketch it out. So that would have been this right there. So that's our triangle. And now we want to find what the area is for this. Okay, so if we do want to concentrate on this area, let's call this area, you know, 1. So that would have been for this area. So area 1, okay, which is that triangle AB and E. All right, so now if we're looking at this particular graph, we should kind of remember what the area of a triangle is. So this is 1/2. Right? And this is going to be your base times your height of the triangle, okay, that you have in here. So that's your base times your actual height of the triangle. Now, in this case, well, we have a 1/2 right here. Notice that the base itself, and so that would have been, okay, this, okay, so from here, okay, all the way up to here. So notice that's 3. And because they want the units, you know, so we can actually grab the units over here. So look at this, and this is in seconds, okay, and then this, notice that it is in meters. Okay, so in that case, what we have is, okay, so this is 3 seconds right there. So that's what we would have over here if we wanted to be able to find the base. And now if you want to be able to find, okay, the actual height. So what you would do is you would just go ahead, okay, and your height would have been from here all the way from here. So as you're moving along in that direction. Okay, so now notice that this is all the way over here. So it looks like it's, this is 10, this is 8. So that's going to be 9, right? So it's basically rising 9 over there. And that is in meters. Okay, so this is what we have. Now, with this, as you're moving along, so that's going to be, well, 3 times 9, so that's 27. So that's going to be 27 divided by 2. Okay, the unit is a little strange because it's meter second. So that's irrelevant, but they do want this unit, so we'll just leave it. And now as you're moving along here, so because of the fact that everything that has been written really just has one significant figure in here. So if you were doing this, let's say if you're popping out your calculators in here, so if you don't feel comfortable in taking 27 divided by 2, so it's going to be 13.5. So if you're not doing any rounding, then that's what this would be. Now, if this has one significant figure and this has one significant figure, then you actually, would round this off to, okay, so this would have been 10. And that would have been your answer to one significant figure for this. All right, so that's the area. So the area overall is, 13.5 if you do not round, and then it's 10 if you do round. All right, so let's now take a look. So this is going to be for B. So if we dive into the second one, so that's this one. Now we want to know what the rectangle is. And notice the rectangle says BC, F, and E. So BC, F, and E. So that's going to be this rectangle right here that we have. It's almost like a square, but keep in mind that the units are a little bit different. Oh, it didn't do a right one for me, but okay, so that's what the square is there, or the rectangle is there. Okay, so, well, for rectangles, certainly is a little bit easier for us. So the area, let's call this area number 2. And that's just simply your base times height, or length times height, or length times width, whatever it is, okay? So length times width, or whatever it is that you want to be able to call that. It doesn't really matter, but you know that you're going to be dealing with one and the other, and we have to multiply those two. So we are moving along here. So notice that right here, so this is at 3 seconds, and then right here, so this looks like it's at 7 seconds, right? So 3, 7, so that's going to be 4, and that's going to be 4 seconds, and then multiplied by the height, well, it's kind of going to be the same height as we had in the previous one, which is going to be 9. So this becomes 36. Right, so this is 4 times 9, 36, and again it's meters second. So strange unit for the moment. Okay, and those units just simply multiply one and the other. Now, if you want this to only one significant figure, then the answer would have been just simply 40. All right, so that's the area for that. Well, now the last one, as you're moving along, so for this one, so that will be this one, that's the quadrilateral there, CDGF, and this one is actually interesting. So you're going from here, right, to here, okay, here, and then you have this. Now you don't have to actually remember what the formulas are for these quadrilaterals. In fact within physics, just make your life easier. So you can split this up. So this is basically going to be like a composite shape in between two. So you're going to have a triangle, and then you're going to have really a rectangle at the bottom. So it's very easy to be able to do that. So let's call this one, let's maybe say this is A3, and let's call this one A4. So those are the areas, and you can just do them one at a time. So it's not very difficult to be able to do that. Okay, so let's jump in here. This is going to be for part C. So let's say, let's make this one the first one. So that would have been, so this is coming from 7 all the way up to 10. All right, so that's going to be 3. Okay, so seconds of a change. And then as you're going up, so it's going to be up to here, right? So we need the actual height, okay, all the way up to the top. So that's going to be from 0, and it looks like on the left-hand side, it goes like all the way up to 5. So that goes right there. So that's that. and this is going to be 15. All right, so again, these units that we have. Now I'm not going to round anything as of yet. Okay, let's bring in area number 3, and then let's add them together at the end, and then you can round. Don't round anything in the intermediate steps for yourself. Okay, so within here at all. All right, so what do I have? Well, it's a triangle, so this is going to be 1/2. Now, the base actually is the same thing, so it's going to be still 3 seconds. So that's the same kind of base that you have. Now, the height is going to be from 5 to 9. So that means it's 4, because it's 9 minus 5, so that's 4. And that's going to be 12, and then 12 divided by 2 is just 6. Now, we're going to, of course, add these together. So you're going to be adding this one, and that's going to be 21 meters per second. And if you wanted to round to only one significant figure, then it would have been 20. All right. So this is what you have. Now, just one comment, if you're going to be writing M and S together, so if you write it, sometimes you might think that it's milliseconds, so just be careful. So for all of these units, okay, that I have written, very often, okay, if you have this, you can just put a little dot right there so that it just separates this so that you know that it's meters and seconds. Because if you do indeed write it as I did over here, then someone might think that it's meters, milliseconds. All right. Okay, so that's another question for you. All right, so question number 3. So find the slope. Now it says round to the 10th if necessary. All right, so we'll try to do that. Well, this one's going to be much simpler. So in terms of your slope, so recall, so this is going to be your rise over your run as you're going through here. Well, so if your rise is 24 meters, okay, your run, it's telling us it's 5 seconds. All right, so this is what we have in here. So now you can take this out. Okay, so rounding to the 10th, so 24 divided by 5, and that's 4.8. So that's already to the 10th. Okay, so there you go. Now, notice this is meters, seconds. There's no directions or anything like that. So this just looks like it's some kind of a speed. All right, so that would have been for part A. Now for part B, we have, so the same thing. This is would have been your rise over your run equal to, now notice that the unit they want in kilometers per hour. So we have to kind of be careful because this is in kilometers, but this is in minutes. So, we have to kind of keep that in mind. So I'm going to keep the unit in here. So this is -14, that's your rise, kilometers. And then your run, which is 35 minutes. So this wouldn't be what we would want to have it. So we kind of have to change those minutes. So this goes back to unit conversions. So we know that 60 minutes is equal to 1 hour. So I'm going to just do that to cancel this off. And then I'll have my hours in the denominator. All right, so for this one, so what would we have? Now we know it's going to be negative, so I'm not going to input that in here. So it's going to be 14 divided by 35. So that's our 0.4 right there. And then we have to, multiply it by the 60, which we just did. So this is going to be 24. Now, since they wanted to round to the 10th, all right, so, you can put this right there. So 24.0, so that keeps it to the 10th. Now it says if necessary, so you could have left it at 24. And this would have been kilometers per hour. And then don't forget the negative, so we can put that negative there. Again, we don't know any directions, so this looks like it's just some kind of a speed. And it looks like it's, because it's negative, so what that means for your speed, typically if it was velocity, it just means you're going in the opposite direction to whatever you made positive. All right, so that's another example for you. Here's an interesting question. So a question that says, identify the measurement if the measurement is a scalar or a vector, and then how do we know that? Okay, so, well, I'll answer the second part actually first. So how do we know that it's a vector? Whenever you're given a measurement, so this is any measurement that you have, and measurement always will include, it will have some kind of a numerical value, right? It's going to have a unit. And then, one of the third things that you will need to know if and this third thing tells you if it's a scalar or vector. If there is a direction, which is attached to the measurement, then you know that it's a vector. If there is no direction at all attached, then you know that it's a scalar. All right, so it's actually relatively simple. So I'm going to kind of label them off, and let's make this, okay, let's first attach all the scalars. All right, so scalars have no direction. So that means A is going to be a scalar, and just kind of moving along. All right, and it looks like D is also going to be a scalar, just the way that it's written. So it has a measurement value with regards to a numerical value and a unit, but there's no direction. And that means that all the other ones, okay, that we're going to be running into are going to be vectors. So this is a vector. Notice there's north. This is a vector, so it says at 45 degrees. Okay, so that's what we have there. And then this is a vector because it's there's a south which is attached there. So that's how you would tell that it's a vector, okay, or a scalar if you are given some kind of a measurement. Here's another question. So what is the displacement if your DI, so notice this is your initial position, so DI just stands for initial, and so that's what we have, and it says negative 8.2 meters east, and then DF is equal to 25.1 meters east. So if you're looking for the displacement, so your displacement, okay, what you have, so that is the change, and that would be the change, and this is going to be, so now this is going to be a vector, so this is what we will have, and this is what you're going to deal with. Now, I want to just show you this visually as well, so what happens. Okay, so since they're, talking about east, okay, so here's east, so that would have been, to your, well, I don't know, depending where you are, okay, I'm going to draw, we typically, if we have just a two-dimensional plane like you're watching the video, it's going to be to the right. So east is in this way, and you're going to have some kind of a 0 in here. So that's, now of course this will just be arbitrary, but you can just define it how you like in terms of positioning. You can think of this as being your x-axis, for instance. Now initially it says it's at negative 8.2 meters east, right? So if you're, if you're thinking about that, so well, negative 8.2 meters east, that negative just means that it's that vector, right, is actually on the other side. So it's going to be right here. So that's going to be negative 8.2. Okay, so it's actually on the other side. Okay, as you're kind of moving along, and this is all in meters, by the way. And then your final one, which would have been all the way now. It's going to be much further than this because it's not scaled, but this is, okay, 25.1, and this is on the positive side. So when the numbers are positive, okay, it's going to be on the positive side, on the east side, right, with respect to the 0. And if it's negative, just means it's actually, okay, the opposite vector, right? So really, this right here, if you were writing this down, if you write negative 8.2 meters east, okay, this is the same thing as saying 8.2 meters west. Okay, so if your origin is starting here, this is, if you have been walking west over here. So these two are equivalent, so that's why you can see there that I put negative 8.2 on the other side. Now when you're doing the displacement, please make sure that these are actually aligned, so your directions are aligned. So I cannot use west and east together, I would have to switch them back. So what that means is that if I'm going to be substituting this into here, change the color, so that means my final one, so this is 25.1, it's all in meters, it's all east, so this is all great. Okay, and this is negative, and now I have to be careful. So this is subtraction, and this is going to be negative 8.2. So this and this, okay, so for math that cancels up to a positive. So this is a positive, this is 8.2. And now you can go ahead and add these up together, right? So you can take out your calculator or just write it down regularly, what you have. So this is going to be 33.3 meters, and it is east. So it is a direction, and this is your displacement that you have. So that means you've displaced, 33.3 meters, okay, in total. Now, in terms of rounding, so be careful here. So if you're going to be doing rounding, this has two significant figures, the 8.2, and 25.1 has three significant figures. So we're going to be rounding to the smallest amount, which is 2. So that means our answer rounded would have been this. All right, and that's your displacement. All right, so there you have it. Thanks for watching.